mass of the tin cup. Specific heat capacity of tin. Do I know the specific heat capacity of tin? Yes, data booklet, right? Can somebody just double check? I think it's 0.227. Is that it? Okay, so 0.227 joules per gram degree Celsius. And of course, the temperature change. Now, this is where it gets a little, not confusing, but do I have a temperature change for the tin cup here? If you look through those data values there, do you have a temperature change for the tin cup? And the answer is you do. You have to assume that it's the same as the temperature difference in the water. Because if you're heating up the tin cup, you're heating up the water. Okay? If the water goes up from 19.8 to 42.6, then the tin cup is also going up by the same amount. Okay? So 42.60, I don't know, where can I do this here? I'll do it over here maybe. Delta T, 42.60 minus the, what was it initially? 19.8 is the the final minus the initial, right? So those differences. That works out to be a negative 22.8? No, 8 degrees Celsius. Is that right? Can somebody just do that real quick? 42.6 minus 19.8, just to double check. Yeah? Oh, sorry, positive, yeah. Positive. Is that good, though? 22.8, yes? I think so. Yeah, okay. 22.8. So, yes, I realize that the water is going up by that temperature, but so does the tin cup have to go up by that temperature as well. We have to assume that the energy that's gained by both of them, okay, equally. So, and what about the mass of the water? Okay, now we have to focus on the water part here. Do we know the mass of just the water? Okay, and the answer is we can find it from this information. Remember, if you have the mass of the tin can and the water is 195.49, the mass of the tin can is 70.32. Well, if we subtract those two, we of course get the mass of just the water, right? That's what we want here, mass of just the water. So once again, right here, I'm going to do my, what is it, 195.49 minus 70.32. So right here, 0.12517 kilograms. Water, 4.19 joules per gram degree Celsius. Temperature change, same, 28, 22 Celsius. That's going to equal. I ran out of room here, of course. So we can subtract those two numbers, 221.50, and subtract 220.88, and we get 0.62. So 0.62 grams is how much we burned, okay? How many grams we burned. And the molar mass, of course, to calculate moles, well, it's methanol, CH3OH. So we need what? Let's see here. Carbon, 12.01, 4 hydrogens, and an oxygen. 32.05? Sounds about right, I think. 32.05 grams per mole. Okay? And of course, we have our delta CH here. Calculating all that, and if you're not sure about if you're going to do this right on the calculator, maybe you should do this. Okay? It's up to you how you want to do it, but basically you got all your left side information here. You can put that all into your calculator first, exactly like you see it there. It probably should work out just fine. 0.070 22.32 times 0.227, times 22.8. We're going to add to that some 0.12517 and 4.19 and 22.8. And on the left side, you should get 11.99, I believe, if I'm not mistaken. And let's just double check this here, because why does that number sound different? 0.12, oh, there we go. Sorry, no, that's not right. I screwed up on a number there. 0.0707032 times 0.227 times 22.8 plus 0.12517. That's where I screwed up. 4.19 and 22.8. There we go. 12.32 on the left side. Okay. We're going to divide that by, of course, the moles. So on this side here, you get kilojoules, of course. Yes, kilojoules. And over here, you get the moles, because I'm taking the grams divided by the molar mass. Grams divided by grams per moles gives you moles. So dividing all that, your final answer here should work out to be, just give me one seckie here. 32.05, right, molar mass? Is that right or no? Yeah. Carbon, 4 hydrogens, oxygen. Yes? Yeah. 636.95. Yes? Is what you should get for that. Yeah, maybe that's what I got. We probably need to go to 637. Sounds about right. Kilojoules. Okay. 3 significant digits. I think the temperature is the one that's going to kind of hold you back a little bit once you do the subtracting those two numbers. 22.8 is only 3. So probably 3 in your answer there. Okay. And this would be, of course, kilojoules per mole, of course. Right? Kilojoules per mole. You're finding the molar enthalpy of combustion, in this case of methanol. Okay? Questions on that? Nothing really different. The only thing is there's another MC delta T there that you need to worry about. That's all. Okay? Same thing we did before. Yes? Questions? Anyone? Yes, no? Okay. Now, next, we need to calculate also, let's see here, kilojoules per mole and kilojoules per gram as well they want here. So the molar enthalpy of combustion in kilojoules per gram, which is also sometimes a common question here. To change this to kilojoules per gram, there's a couple ways you can do it. Okay, you could actually go back into this original equation, do the exact same thing, but instead of using the molar mass here, you could just use the 0.62 grams, okay? Divide those two out and you'll get kilojoules per gram, so that's an option. But I like you guys to figure out kilojoules per mole, so there's options here for you guys. But listen, if you have 637 kilojoules per mole, per 1 mole basically, right? That's what that means, right? 1 mole of methanol is equivalent to saying 637 kilojoules for 32.05 grams, right? Because the molar mass of methanol is 32.05 grams per mole of it. Well, instead of saying 637 kilojoules per mole of methanol, isn't it the same thing to say, aren't these two the same thing for methanol? 1 mole is 32.05 grams, yes? Molar mass. So if I take 637 kilojoules and divide by 32.05 grams, okay, I will get, I believe it was 19.9 kilojoules per gram would be my other delta CH in kilojoules per gram, okay? Once again, look, right here, 32.05 grams for every mole of methanol that you have, okay? So in this particular case, you have 1 mole, 32.05 grams, divide those two out and you will get the molar enthalpy in kilojoules per gram. So replace the 1 mole with the molar mass, basically, the 32.05 grams, okay? And there's your 2 answers for that. Yep. Yep. Yeah, because you're not only putting the same heat into the water, you're putting the same heat into the metal tin as well. Now, the energy that is associated with that will be different because you have different specific heat capacities for that. So that's where people get confused. They're like, well, doesn't tin heat up differently than water? Yeah, it does. But that's a specific heat capacity. They both increase by the same temperature, but the energy you get out of that is different, right? Because Q equals MC delta T is going to be different for water than it is for tin, for example. Okay, and that's where the specific heat capacity thing comes in. Okay, so that takes care of that. You have to assume that they both heat up the same. Yeah. Okay, good. Questions? That's flame calorimetry, so that's what you're going to do tomorrow. MC delta T, MC delta T. Next, we're going to talk a little bit about bomb calorimetry. Boom. No. Okay. Bomb calorimetry looks like this, okay? And basically a typical bomb calorimeter looks something along this line here. You have, it's a metal container. You have a thermometer stuck into there. You have a stirrer right here. So you have actually a piece of a stir rod in there that actually turns by itself. You have a wire for ignition. You might say, well, why is that? This contains pure oxygen in here, so only oxygen. And you would put your reactants or your fuel in there. And basically you would light it to a source. So you'd give it some electrical energy. It would combust, and the surroundings would absorb the energy. But when you look at a bomb calorimeter, there's many, many, many parts to it, okay? If you look back at the flame one, well, it's really just the water and the can, yeah? You know, here, you got lots of stuff here. You got, for example, is this glass stir rod, could it absorb some energy? Possibly, yeah. Is the surrounding container going to absorb some of this energy? Yes. What about this bottom part here? Maybe it's not made out of the same metal. Is that going to absorb some of the energy? Sure it is. The water will absorb energy. What about this magnetic stir rod? Is that going to absorb some energy? So how many times are we going to do MC delta T for these? Well, I guess it depends on how much stuff we have in there, yes? Because it's all the same stuff, guys. You're going to burn something, and the heat's going to be transferred. Well, MC delta T for the container, MC delta T for this combustion chamber, MC delta T for the magnetic stir, MC delta T for these wires perhaps even, if they're made out of metal, MC delta T for the water, MC delta T for this, MC delta T for that. You might end up with 7 or 8 of them, yes? True? Right? Because all those things could absorb the energy. And we need to conserve all that energy that we made, so all those things might be absorbing it. So that's a lot of MC delta T's. So with bomb calorimetry, we don't talk about MC delta T, okay? We talk about basically the whole bomb calorimeter as a whole. So they've calculated that for you, so you don't have to do MC delta T 10 times or 7 times or even 5 times. They're going to give you basically MC delta T in a slightly different way. Okay, the combustion reaction that takes place in the intermetal chamber, the bomb which contains pure oxygen. This didn't really work out on mine here. To measure the heat precisely, you must know the heat capacity of the calorimeter. That is measured in big C. Okay, so we no longer have a specific heat capacity for a metal or water, little c. We have for the whole bomb calorimeter, big C. And big C is measured in kilojoules per degree Celsius. So when you see kilojoules per degree Celsius, the only thing that associates with that is a bomb calorimeter. Okay? So you have to know that. Pick up on that quickly. Okay? And that's what C is measured in. So heat capacity, or big C, is measured in kilojoules per degree Celsius. Not joules per gram degree Celsius. There's none of that in this bomb calorimeter. It is simply kilojoules per degree Celsius. This might even be easier than anything else we've done. Okay? So let me show you some examples here. The heat absorbed by the calorimeter during the combustion of the fuel can be found by this. This would of course be kilojoules this is your specific, well, they don't really actually call it the specific heat capacity of the bomb calorimeter. They call it the heat capacity. This is measured in kilojoules per degree Celsius, and of course your temperature changes in degrees Celsius. Okay? Q is one side of the equation, just like before. What's the fuel that's burning it? N delta RH, or N delta CH in this case, I guess, combustion. Okay? So we have this maybe perhaps on one side. We have N delta CH on the other side. Energy lost equals energy gained. Okay? So we don't have to worry about a bunch of MC delta T's here. This is your equivalent to, this right here is actually your equivalent to MC kind of thing in a flame calorimeter. You don't have to write that down. That's equivalent to the flame calorimetry kind of part. Okay? They've included all that stuff. They figured it all out for you. Here's the heat capacity of this bomb calorimeter, 14 kilojoules per degree Celsius, and then how much does the temperature rise by? Okay, so let's take a look at an example here. General equation. So kind of what do you expect to see here? Something like this here. Fuel, as always, on this side. This is your E lost. The energy that's gained is a big C delta T. Big C, of course, remember, refers to the bomb calorimeter. So when you see that, you'll know that. You're not going to find those numbers in a data booklet anywhere. They will have to tell you in the question. So when they tell you in the question, and it's kilojoules per degree Celsius, you say, hey, that's a bomb calorimeter. Easy. Okay? So let's take a look here. Naphthalene has the formula of C10H8. When 1.58 grams of C10H8 is burned in a bomb calorimeter, has a heat capacity of 8.57 kilojoules per degree Celsius. Calorimeter's temperature increases by 7.42 degrees Celsius. Calculate the molar enthalpy of combustion for C10H8, kilojoules per gram, and then finally a balanced chemical equation. Okay, now let's do that. So where's the numbers here for that? So here we go. E gained here equals E lost. Once again, on this side here, you're going to have your fuel that you burn. How much fuel am I burning? How many moles do I burn? And on this side here, there is no, like I said, MC delta T, because it's in a bomb calorimeter, so I need to know the specific heat capacity of that bomb calorimeter. Specific heat capacity of this bomb calorimeter turns out to be 8.57 kilojoules per degree Celsius. It increases by a temperature of 7.42 degrees Celsius, that bomb calorimeter. So if you look at the units there, Celsius, Celsius cancels, you got kilojoules left. That makes sense. That's how much heat was generated on that side. On this side here, I have 1.58 grams. And of course, I need to know the molar mass of C10H8, which works out to be, I forget now, 10 times 12.01 and 8 times oxygen, or hydrogen, I should say, 128.18 grams per mole. Okay? Solve for delta CH. Obviously, we're going to end up with a negative here, right? Negative on that side, so let's see here. 8.57 times 7.42, oops, 1.42. We're going to divide that by our 1.58 and dividing by 128.18. We should get a negative 5158.79 kilojoules per mole, molar enthalpy. Okay? Significant digits. We've got to go back and look at the question. The question, I think, has 3 significant digits, kind of from what I remember, if I'm not mistaken. So let's take a look. 3 significant digits. I guess my best final answer would probably be negative 5.16 times 10 to the 3rd kilojoules per mole. Final answer. Okay? Good so far? Yes? Okay. Second part was, let's calculate that in kilojoules per gram. So how many kilojoules per gram would I expect to get? Or how much heat would I expect to get for each gram that I burn here? Well, you know, once again, I'd probably take this unrounded number here, guys. Probably is what you should do, unless it specifically tells you to take this one, but unrounded number, still my calculator there. If I had negative 5158.79 kilojoules for 1 mole, well, that's kind of like saying negative 5158.79 kilojoules per 1 mole of C10H8 is equivalent to 128.18 grams, right? Molar mass. 1 mole of C10H8 is the same as saying I have 128.18 grams of C10H8. So if I divide it by 128.18, I get a negative 40.2 kilojoules per gram of C10H8. So for every gram I burn, I should get 40.2 kilojoules of energy. All right? Good so far. We have one last thing to do. Yes? Good? Questions, anyone? Balanced chemical equation. And obviously we want to include probably molar enthalpy. Wouldn't be a bad idea for review there in case. C10H8, which happens to be a solid, oxygen, let me move this up a bit here, gives you carbon dioxide and, well, water. But listen, this is not in your notes. It's actually a little bit later in your notes, but I might as well tell you about this now. And does this make a difference? And the answer is, oh, sure does. In a bomb calorimeter, carbon dioxide is going to be a gas. That's fine. The water, it's inside a closed container. So the water doesn't have a chance to really vaporize, and any water that may vaporize still is in a closed container. So it turns out that water in a bomb calorimeter turns out to be a liquid in this case. And I'm going to write that down here. Bomb calorimeter. And we'll take notes on that a little bit later there. But in a bomb calorimeter, if you're doing equations for bomb calorimetry, that water is a liquid. Okay, you have to remember that. Usually on the diploma, they'll remind you, they'll tell you that the products are carbon, they might even tell you the products are carbon dioxide gas and water liquid. Does it make a big difference? The answer is yes, it does. We're going to do Hess's law next, and Hess's law has to do with different states and whatnot, and heats of formation and stuff like that. So it does make a difference. Okay, so you have to remember with a bomb calorimeter, water's a liquid. Okay, balancing, 10 carbons, 8 hydrogens. 4 times 2 is 8 hydrogens. We got 24, and half of 24 is 12. Okay, if we want to include the the enthalpy change as part of this balanced chemical equation, which you should be able to do, of course, right there I put in delta H is a negative. Okay, let's use obviously delta H. We talk about kilojoules. So for 1 mole, right, because this is a 1 here, balanced chemical equation, we get 5.16 times 10 to the 3rd kilojoules per every mole that I burn. Based on this balanced chemical equation, I'm burning 1 mole. So over here I'm going to put negative 5.16 times 10 to the 3rd kilojoules. Okay, and that should go at the end of the equation, but of course, smart boards aren't wide enough. Okay, good? Questions, anyone? Questions? Ask if you're not sure about anything. That's flame. Flame involves MC delta D, MC delta T, maybe even more, depends on what you all got in there. Bomb is a different type. Okay, bomb is inside a combustion chamber, all enclosed, everything else. Okay, so keep that in mind. Tomorrow in the lab, we're going to do flame calorimetry. Okay, so you're going to do 2 different fuel sources, and you're going to compare them, kind of thing. Okay, so good. Questions, anyone?